Welcome back. In this lecture, we will look at a defining aspect of solid oxide fuel cell. It has to do with the nature of ion transport in the electrolyte of a solid oxide fuel cell. As a general introduction, the different types of reactions that are in different fuel cells have already been addressed. Please refer to this lecture. We are mainly looking at two kinds of fuel cell. In the last few lectures, we looked at PEMFC. In this lecture and the next lecture, we will look at solid oxide fuel cell. As opposed to PEM fuel cell, in SOFC, water is produced at the anode. In a PEMFC, cathode is the electrode wherein water is produced. This is one central difference. As I stated in the earlier lecture, proton conduction is rather special because of many mechanisms involving quantum mechanical tunneling. This makes proton conduction very facile, and proton conducting membranes are typically have greater ionic conductivity. In an SOFC, oxygen anion is the ion that is being conducted in a solid electrolyte. In a proton exchange membrane fuel cell, the electrolyte is a semi-solid polymer, but in an SOFC, the electrolyte is an inorganic membrane and it is a solid electrolyte. And typically, the conductivity that you can get from an oxygen conductor is always less than the conductivity that you can get from a proton conductor. But SOFC has an advantage of operating at rather high temperatures, which significantly enhances ion conductivity. So there are three major classes of electrolytes that are used in SOFC. We would mainly be looking at this class of electrolyte. This is the dominant class of electrolytes. As you can see, the temperature of operation of solid oxide fuel cell is rather high. It is around 700 to 1000 degrees centigrade, which has its own challenges. How to reach such high temperatures and how to handle high temperatures without material degradation is a significant challenge, but it also has certain advantages. One is that the conductivity can be rather high because of high operational temperature. The anode and cathode O potential is significantly lower, and it is possible to have low activation O potential even with non-noble materials because the fuel cells operate at high temperature. That is, the SOFC operates at high temperature. So we will be looking at this particular class of electrolyte, yttria stabilized zirconia. On the other hand, there is another class of electrolytes which is also interesting, which operates at rather low temperature if you consider this particular temperature, but it has certain disadvantages. We will look at it in the next couple of slides. There is an advantage with respect to zirconia. First, it has low intrinsic conductivity. Typically, when oxides have certain conductivity, the conductivity can be due to oxygen vacancies. Many of the oxides are N-type electronic conductors, and it is not desirable to have electronic conductivity in an fuel cell electrolyte. Therefore, it is better to start with a material which has low intrinsic conductivity. And the additional feature which is important is that zirconia at room temperature has a monoclinic phase. At moderate temperature, there is a phase transition to a tetragonal structure, but the structure that is of interest at high temperature of SOFC is a cubic structure. It has a it is good to have review your solid state chemical structures. So if you're unfamiliar with all these structures, especially if you're unfamiliar with the fluoride structure, please refer to this wiki link to understand what is a fluoride structure. So in zirconia, oxygen anions occupies tetrahedral interstitial sites in an FCC cubic fluoride structure. Because it has low intrinsic conductivity, which I said is desirable for certain reasons, which we will look at in the next few slides, the conductivity of zirconia can be modulated by doping with yttria. This is very much like why silicon is useful in semiconductor industry. Silicon, pure crystalline, single crystalline silicon has low conductivity. Therefore, a perfect silicon is not useful in terms of semiconductor science and technology. However, because we can modulate silicon conductivity by doping, silicon or doped silicon becomes useful in semiconductor science and technology. Likewise, even though zirconia has low intrinsic conductivity, therefore appearing uninteresting, its conductivity can be modulated by yttria, making yttria stabilized zirconia quite interesting material for ceramic based applications, especially in the case of solid oxide fuel cell. As opposed to zirconia, which is a tetravalent ion, yttria is a trivalent cation. Why this is important is because when yttria substitutes for zirconia, that is, when zirconia is substitutionally doped with yttria, when you have a trivalent cation replacing a tetravalent cation, the bond between the cation and oxygen is weakened, and this leads to the formation of oxygen vacancy. So when a lower valent cation substitute in place of a higher valent cation in a host oxide, the bond between cation and anion is weakened, thereby promoting oxygen vacancy formation. We'll see why this is important. In addition, when you substitute yttria in the place of zirconia, this FCC cubic fluoride structure is stabilized more easily in a doped zirconia structure. When such a phenomena is possible, the advantage is that it is possible to form a cubic structure at relatively lesser temperature than what it would have been possible with pure zirconia. Supposing that's what that's what we mean by yttria stabilizes zirconia in the cubic structure. So doping has two advantages. One is that it promotes the formation of oxygen vacancies. It promotes the stabilization of the cubic structure. If you can form a cubic structure at a lesser temperature, the challenges of high temperature operation is lesser, and it is possible to avoid material degradation at a relatively low temperature compared to what it would have been without doping yttria. So when this is the oxide composition, if you have yttrium oxide, this is like Al2O3. Al is a trivalent cation. Likewise, yttria is also a trivalent cation. Therefore, it forms a oxide of composition Y2O3. When yttria is substitutionally doped into the zirconia structure, it promotes the formation of oxygen vacancy. Why is this important? When you want to transport oxygen anion in an electrolyte, this transport is possible only in the presence of oxygen vacancies. So when we say oxygen anion, so in this schematic, this refers to the oxygen anion that is getting transported. It will get transported only to an adjacent site wherein oxygen vacancy is present. So when we say that oxygen anion is getting transported, for example, in this direction, effectively what is happening is that oxygen vacancy is getting transported in the opposite direction. If you look at these structures, oxygen anion gets transported to an adjacent site wherein an oxygen vacancy is present. So this is pretty much like what happens in a semiconductor. When you say a hole is getting transported in a particular direction, what is happening is electron is actually getting transported in the opposite direction. So electron transport is inherently coupled to hole transport. Likewise, an oxygen anion transport is inherently connected to an oxygen vacancy transport. We have already looked at the conductivity of an electrolyte in previous lectures. We gave this formula for conductivity of an electrolyte. This refers to the charge of the ion. Ui refers to the mobility of a concerned ion I, and Ci refers to the concentration of that particular charge species I. When you try to apply this kind of equation for these kinds of material, the mobility which we are referring to is inherently connected to the mobility of oxygen vacancy migration or oxygen vacancy transport. This transport also involves activation barriers, and therefore at a higher temperatures, these activation barriers can be crossed more easily. The charge also refers to the charge that is present in the oxygen vacancy. That is, if you are familiar with the Kruger ring notation in ceramic literature, the charge of the vacancy is also clear, must be clear to you. For example, the charge here will be 2 minus when you say oxygen anion is getting transported. Concentration again refers to concentration of oxygen vacancies that are getting transported. So this relationship suggests that the conductivity is linearly proportional to the concentration of oxygen vacancies. This is not quite true. It is to an extent true, that is in the sense that if you increase the oxygen vacancy concentration, let's say at low concentration, conductivity does seem to increase. Or if you increase the charge associated with the vacancy, the conductivity does seem to increase. However, there is limit to this behavior wherein conductivity linearly scales with concentration of vacancies. This is because in these kinds of electrolytes, there is strong interaction between the vacancy and another vacancy. That is, each vacancy is not independent of other vacancies. In this formula, when we derived, we more or less considered the charge carriers to be independent of each other, Therefore, conductivity contribution from each of the ion could be added up very easily. However, in these kinds of materials, the vacancies interact strongly with each other. So typically, when we say yttria is doped into zirconia, the concentration of yttria is about 8%. So these are not very small concentration of vacancies. So at this concentration of vacancies, the interaction between the vacancies is also considerable. But what is important to understand is that the conductivity is critically dependent on temperature. So this is like an Arrhenius plot. So you are plotting conductivity versus 1 by T. So along the x-axis, temperature increases in this direction. So what we see is that there are 3 different classes of electrolytes. So the main focus here is on yttria stabilized zirconia. So for every substitutional replacement of zirconia by yttria, one vacancy is generated. What we see here is as the temperature increases, so that is in this direction, as the temperature increases, the conductivity also increases. This is in log scale because this is an Arrhenius plot. So 2 main points. It is important to have vacancies, and one can create vacancies by substitutional doping of zirconia with yttria. At low concentration, conductivity does scale with vacancy concentration. But more importantly, an important determinant of conductivity is the temperature. It is possible to increase the conductivity significantly. Okay, so this is log scale, mind you. So it is possible to increase the conductivity significantly by increasing temperature. That's why if you, instead of operating at 600, if you operate at 1000, the conductivity is couple of orders more in solid state electrolytes. Moving further, another important aspect is that whenever we have an allovalent doping, what do we mean by that? That is, the dopant has a different charge. This is a trivalent dopant that is substituting for a tetravalent host cation. This is called allovalent doping, as opposed to isovalent doping. When you do dope isovalently, if the host cation has 4+ charge, the dopant that is substituting also has a charge of 4+. In an allovalent doping, there is a charge mismatch between the dopant and the host cation. Whenever you have an allovalent doping, it also increases electronic conductivity to some extent. What is not desirable is to have electrical conductivity, electronic conductivity. If there is significant electronic conductivity, then shorting between anode and cathode is possible, because there's an electronic pathway between anode and cathode, which is very highly undesirable. For example, in a lithium-ion battery, the reason why you want to be avoiding dendrite formation is that dendrites provide for electronic conductivity across the electrolyte, thereby increasing the chance of shorting of the anode with the cathode. You want the electrons to go only via the external wire and not via the electrolyte. So it is always better, it is always important to have only ionic conductivity in the electrolyte. So in this case, because you have allovalent doping, there is some chance of electronic conductivity. And if the electronic conductivity is very less, it is advantageous. So what you see is that in the case of, let's say, yttria stabilized zirconia, ionic conductivity divided by electrical conductivity. So electrical conductivity has two parts. One part comes from ionic conductivity. This sigma refers to electronic conductivity in the electrolyte. You don't want this. If this is zero, that is ideal. But however, because of aliovalent doping, it is not possible to have zero for electronic conductivity. But the transference number is more or less one. That is, all the current that is being carried is carried by only the ions, and very limited current is carried by the electronic conduction pathway. As opposed to, let's say, yttria stabilized zirconia, ceria has much lower temperature of operation. As was mentioned in a previous slide, the temperature of operation of ceria electrolyte is about 600 degrees centigrade, which is at least 200 to 400 degree less than yttria stabilized zirconia. The reason for this lower operational temperature of ceria electrolyte is that the oxygen anions are very mobile in ceria as compared to oxygen anion mobility in yttria stabilized zirconia. However, even though this is advantageous, that is, you have greater mobility of oxygen anions in ceria, therefore lower operational temperature. But the disadvantage is that in ceria, there is significant amount of electrical conductivity because of electronic conductivity. That is, the sigma in ceria is higher than sigma in YZZ. So these are certain trade-offs that you see in different kinds of electrolytes. So one trade-off is that you have lower operational temperature because of greater mobility, but while that is an advantage, the lower transference number of current carried by oxygen anions in ceria is a disadvantage when it comes to ceria as a solid state electrolyte in an SOFC. In the next lecture, we will look at the different OO potentials that you commonly observe in a solid oxide fuel cell. Thank you.